Right, my name is Chan. I'm from Cisco Networking Academy. This is our website. Please feel to visit our website. Today we're going to talk about digital transmission, mainly about line coding. So whatever information that you have, you either need to transform it into a digital signal or analog signal, so that then only you can send across it. So in digital signal transmission, we talk about how do you convert digital data into digital signal, and how do you convert analog signal to digital signal. So line coding is a process. Suppose you have a data, you change it to a line code, and then you send out, and then this is how it looks like in the wire, on the wire itself. Normally when you send it, normally it will be in serial, okay? Communication is always in serial. Alright, so what is a DC component? Okay, there's two important things about in line coding. First is a DC component, undesirable residue direct current. Okay, so the purpose of communication, which you can see here. So you can see here, from here you can see there's a energy being transmitted. Okay, let's right. So if you have a circuit here, and you send a circuit here, if you send a signal like this, right? Let's say this is 0, this is 5 volt. All these are positive energy, correct? Correct? So you are actually, A is providing power supply to B. Right? We don't want that to happen. What we want is that we want to have the amount of energy sent and received, the positive equals to negative. Alright? We want it to be balanced. Okay? So that is, you call it a DC component. But if you send the signal like 5 volt and 0 volt, there always be a DC component. So what you're going to send is you're going to send 5 volt and negative 5 volt, right? So in this case, you will have a less DC component. Okay? So the DC component is that the amount of positive and negative should be the same. That is DC component in communication. Okay? So you can see here, this is a signal without DC component, okay? But if you, let's say if you send all 1 or you send all 0, you will still have DC component, alright? You still have DC component. So the next thing we're going to talk about is self-synchronization. Self-synchronization means this one. It means this. Let's say you have a PC here, you have a clock, maybe 10.01 megahertz. This one will be your clock. Okay. You have another PC from the same manufacturer. It might be 9.99 megahertz. There's a difference in it. There's a slight difference in your clock frequency, correct? Every computer, the clock frequency is different. So if you send something like this, let's say you send 1001 symbol, Once it reaches here, you only get 999 signals. Right? You don't want this to happen. So how do you prevent that? You should put the timing information inside the signal. Right? How do you do that? How do you do that? You have to make sure that the amount of 0 and 1 is, you should make sure that at any point of time, any time, the number of 0 is more or less equals to the number of 1. Okay? So let's say you send here 0, 0, 1. So from here is 0 to 1, isn't it? Right? So you know there's a change here, isn't it? You know there's a change here. So this you resynchronize your clock. Okay? Let's say then from here 1, then you have 1, let's say, then suddenly you have 0, isn't it? You have a change here, isn't it? From 0 to 1, isn't it? So you can resynchronize your clock. Okay? So once you resynchronize your clock, even though your clock is not the same, not exactly the same with some shift, you can still send the signal. Okay? But what if you send the signal like this, all 1 or all 0? Okay? What happens if you send the signal all 1 or all 0? Then the receiver cannot synchronize, correct? What happens if your data is all 1? Your data is all 1. So no matter what is your data is, when you change it to your line coding, the number of 0 and number of 1 is more or less the same. So if you can achieve this, then the other end can synchronize. Okay? So you have to play around with your line coding so that there will be some changes along the way. Okay? So there is synchronization. Okay. So self-synchronization means that digital signal, it can be achieved if there's a transition in the signal. As long as the signal, there's some transition, then you can resynchronize. Okay? So example like this, lack of synchronization, let's say you send 1, 1, the receiver think that is 2 1s, alright? So additional bits is inserted, which you don't want. Okay, so in line coding you have unipolar, polar and bipolar. Okay. Unipolar coding is like this. Unipolar okay, unipolar is like this. 0 volt is equals to 0. 5 volt equals to 1. Alright? You have this one, 0, so let's say this one will be okay. So this is how you send the signal. So first you have a DC component, correct? This is unipolar. So you have DC component because only positive. There is no negative. Okay, there's no negative, only positive. So you have a DC component. Okay, the next thing is what happens if there is a cable cut? What happens if there's a cable cut? Then what you going to send? 0 only, correct? Correct? Then how do you differentiate between a cable cut and you're sending 0? How? Or let's say your cable, you short it with VCC 5 volt. Then you'll be sending all 1 only. How do you know? Okay? Alright, clear? Then there's also some synchronization problem. What happens if you send all 0 or all 1? Then the receiver, after some time, it will be out of sync, right? Because the receiver, let's say here is 1000 hertz. Over here, this one is 999 hertz. After 1000 simple, it will run out of sync, right? If you send 1001. So this is unipolar. Okay, to solve some of this problem, you have a polar. Polar means that instead of this one, you put negative 5 volt. Negative 5 volt, so then you have like this, correct? So you will have less DC component. You will have less DC component, correct? Because you have positive and you have negative. But what happens if you send 1001 or 1000? What will happen? Then the line will be straight only, isn't it? Correct? You have a straight line only, isn't it? So you still have DC component. You still have synchronization problem. Okay, so later on we're going, as the slide progress, then you will talk more about it. Okay. So you have bipolar, which means you use 3 symbol, 0. You also use positive, negative, and 0. Okay. So in unipolar, you have 2 problems: DC component and lack of synchronization. Data contain a long sequence of 1 and 0. Synchronization is lost. Alright. Example like this. Alright. You have DC component. If this part is very long, the synchronization will be lost. Then you have a polar. Polar, you use 2, so you have non-return to 0. Then you have return to 0. Then you have Manchester and differential Manchester. Okay, in non-return to 0, the value is either positive or negative. Okay, so you have 2. One is non-return to 0 L. A positive means 0 volt, negative means 1 bit. Alright, negative volt means 1. Alright, positive. So in this case, you also have a problem if we send a long stream of 0 and 1. Okay, if it's a long stream of 0, then it will be positive only. If it's a long stream of 1, then it will be negative only. So, okay, let's draw it smaller. Okay, let's make the slide bigger a bit. Sorry for all this lack of tools. Okay, in NRZ, so this is non-return to 0. Okay, so meaning that if it's a positive, let's say negative 5 volts, it means 0. Negative 5 volt, it means 1. Okay, what happens if you send all 1? So it will be negative only. Here is 0, the signal. Here will be negative 5 volt. You send like this, correct? So this is all 1. Okay? If you send all 0, then here will be positive 5 volt. This is all 0, 0, 0. The signal will look like this. Okay? So since this is a straight line, you have problem. Right? You have problem. Okay? You have problem on synchronization and also DC component. So then they divide. Then you have what you call a smarter way. You call NRZL inverted. Alright, NRZL inverted. So NRZL inverted. Alright. So in NRZL inverted, zero bit means that there's no change. 1 bit, it means that it changed from negative 5 volt to positive 5 volt, or from 5 volt to negative 5 volt. This means there's a transition. Okay? Suppose you send all 1. Alright? So how will your signal will look like? Your signal will look like this. Okay, so if you send all ones, you got transition in it. So there is no DC problem and no synchronization problem. Okay, if you send all 1, what happens if you send all 0? Let's say from here onwards you send all 0, then it will be like this here. So if you send all 0, right, you will still have DC problem and you still have synchronization problem. Okay? Alright. So it's an improvement. It's an improvement. You can see that? It's an improvement. So now your only problem is you have all 0, you have DC problem only when you send all zeros. Alright? Okay, so you can see here, if there's 1, you can see there's transition. If it's 0, there's no transition. Correct? Okay, to ensure that synchronization, there must be a change in every bit. So what you do a RZ, return to 0. Okay, so what does it mean? Every time you have a 0, okay, in the middle of the signal, you return to 0 bit. Alright, every time in the middle of the signal, you return to 0 bit. So in this case, you use less power, correct? Because you only use half of the power. After that, you return to the 0 bit. Okay, so in this case, you can synchronize every clock cycle. You can synchronize already, correct? Perfect. Eh? What is the disadvantage? Okay, suppose your bandwidth is 10 megahertz, because every center you need to return, so you need to have a clock that is 2 times faster. If not, how we're going to return to the middle, correct? So if you have a clock that's 2 times faster, actually you're using 2 times the bandwidth. Then actually your effective throughput is 50%. You see that, no? Because your bandwidth is 2 times, but then you use it to, your bandwidth is 20 megahertz, but your effective throughput is just 10. So you can see, it requires 2 signal change to encode 1 bit. 2 signal change to encode 1 bit. That means that you use twice the bandwidth lah. Alright? So this is line coding. So the next thing is that you have a Manchester encoding. You use inversion in the middle. Alright? So negative to positive transition means 1. A positive to negative transition means 0. Okay? So Manchester encoding achieve the same level as RZ, but then you only use 2 amplitude. Use 2 amplitude, positive and negative. RZ you use 0 also, né? So this is an improvement. Manchester encoding and differential Manchester encoding is used in the 10 megabits Ethernet. Alright, 10 megabits Ethernet, and I think 16 megabits token ring, they also use that one, if I'm not mistaken. Okay, so you can see this is the Manchester encoding. So this is 0 and this is 1. Okay, how do you know it's 0? Very easy. How do you know in Manchester encoding? How do you know it's 0? How do you write 0? How do you write 0? And Z. Okay, remember? No. 0. So from here, you can see this from, so this is 0. From positive to negative, this is 0. Okay? So if like this is 1. Okay? Alright? 0. Remember, just remember the 0 means 0. Okay? So this is Manchester encoding. I'm sorry because I need to resize. Lacks of tools is like that. Okay. Then okay, so this is Manchester encoding. So no matter what you do, 0, 1, 0, 1, every clock cycle there will be a translation. No matter what you do. Okay? So in Manchester encoding, the transition at the middle of bits is used for synchronization and bit representation. So in this Manchester encoding, you can see the number of 0 and 1, the number of positive and negative is the same, isn't it? Every clock cycle you can see there's changes, isn't it? From positive to negative. So then if there's a changes, then you can resynchronize your clock. Okay? Then your clock will not shift. In differential Manchester encoding, you have present of 0 and absent of 1 of an additional transition at the beginning interval is used to identify the bit. So in differential Manchester encoding, you use 2 signal change to represent 0, but only 1 to represent binary 1. So it's an improvement, because Manchester encoding you need 2 signal change. You see here Manchester encoding, you can see here 1. Okay, this one you also need like this. Okay, alright. Whereas in differential Manchester encoding, you can see here present of transition means 0. So this 0. There's no transition means 1. Okay, so it's an improvement. differential Manchester encoding is an improvement compared to Manchester encoding. Okay, so you should be able to see the difference between the polar, unipolar and polar. Then in okay, the differential Manchester encoding transition in the middle is used for synchronization. Bit representation is defined by inversion and non-inversion as the beginning of the bit. Okay, all right. That is differential Manchester. Then you also have bipolar. Bipolar means that you use 3 levels: positive, 0, and negative. Okay, so one of the thing that you use is A mark, alternate mark inversion. This one I think is used in the ISDN and T1 if I'm not mistaken. Okay, ISDN, T1 and E1 if I'm not mistaken, they uses this line coding. Alright, so this is if it's 1, either positive and negative is 1 lah. Okay, after if 1 followed by 0, then it will be 0 lah. Okay, 0 volt. Okay, if it's 1, 1, 1, then it will swing from positive to negative and negative to positive. If it's 0, you go back to 0. But what happens if it is all the way 0? Then you have a problem lah. Then it will be straight line only lah. There's some problem with the line code. Okay, then they also have some other line coding scheme like 2B, 1Q and MLT. Alright, MLT similar with NRZI. Okay, so this is 2B, 1Q and this is MLT3. Okay, let me recap. Is the line coding. Okay. What is the difference? Or should I do it in the slides? I think I better do it in the slide rather than. Okay. All right. Okay, you have this line coding. First, you have unipolar. So unipolar means let's say 5 volt is 1 and 0 volt is 0. So what's the problem with this one? If let's say you have a cable cut, then does it mean that is sender send all 0 or cable cut? Alright, or you have a cable short to VCC 5 volts. So is it sender send all once or cable shorted? You also don't know. Okay, alright, correct. Then you also have a DC component, okay, and also synchronization problem. Okay, when the sender send all long 1 or long 0s. Okay, you have a DC component because there's no negative voltage. Okay, clear. So this is unipolar. Okay, then you have let's control, and you have here, let's say you have polar. So you have let's say 5 negative 5 volt. Okay, so in this case you have less DC component. Okay, you still have DC component, less DC component because got positive and negative voltage. Alright, so you have DC component. This is what? This is non-return to zero, NRZI, non-return to zero. Okay, so you have DC component when, and synchronization problem when sender send long zeros and long one, correct? So if the sender send long one, that means that the voltage will be negative 5 volts, correct? All the way, right? So it will be a straight line, you cannot synchronize. Okay, alright, then you have an improvement. The improvement will be NRZI inverted. Alright, so in NRZI inverted, 0 means no voltage change. Okay, 1 means that there's a voltage change, either negative to positive or vice versa. Alright, so you still have DC. If the sender send long one, what will be the voltage? Voltage will be negative 5, 5, negative 5, 5, correct? Negative 5, 5, and then negative 5, correct? And so on. Alright? Okay? So there's no DC and synchronization problem. Correct? What happens if sender send long 0? So you still have DC component and synchronization problem. Okay? So how do you improve from there? You use RZ. Okay? RZ. So you use RZ. Okay? So let me look up for the RZ. Okay, let's paste it here. So you can see here. So this is RZ. So you can see RZ. So in the middle of signal, you return to 0. Okay, so then this one, no DC. Okay, because every cycle you return to 0. Every cycle there is a transition. Every clock cycle got voltage change. Alright, so no problem. You won't have DC problem, anything. Okay. But what will be the cost? You need 2 times the bandwidth. You need a clock that is 2 times faster. Okay. That is RZ. Okay, then if you want to be better, then what you can do is that you use Manchester encoding. Manchester, same. So the cost is still the same. The improvement is that the Manchester this one, is that you only need 2 signal change, right, from positive to negative and vice versa. Okay, that's the Manchester. The cost is still the same. You still need a clock that's 2 times faster. 2 times faster means that you have 50% utilization. So then you also have Manchester encoding inverted, okay, differential Manchester, which is in the slide here lah. Alright, in differential Manchester, you require 2 signal change to represent 0, only 1 signal change to represent 1. Okay, a minor improvement. Okay, that's the difference. Then you have what you call a bipolar. Bipole is that you, like ultimate Mach inversion, you use the 0 to also represent positive, 0 and negative to represent the signal. Okay, so that's bipolar. Okay, so then can we do better? Can we do better than 50% utilization? So can we do better or not? So we can do better using block coding. Block coding is used 4B, 5B. Alright, 8B, 10B, 8B, 6B, this is used in some of the gigabit Ethernet. 4B, 5B is used in fast Ethernet. Alright? Okay? So what happens is that you have your data, this data you're going to split it into 4 bits. Okay? All your data you're going to split into 4 bits. Then from 4 bits you're going to change it to 5 bits. And then you put it in the line coding. The line coding you use NRZ. Alright? Okay. So basically you divide all your data into 4 bits. Then based on this 4 bit you're going to map it to 5 bits. And then this 5 bit you're going to put it in the line coding, which is simple. Okay? So you have block 0. This is all 0, isn't it? So then when you map it to become 1110, maximum only 4 0. Only 4 ones. You can see the table here. You can see the table. Maximum there's only 4 1. This one, and maybe this one, and some of this. Okay? So the number of 0 and 1 here is more or less equal. 2 to 3. Okay? So over here is 16 in it. 2 to the power of 4 bit is 16 in it. So we're going to map it into 32, 2 to the power of 35. Alright? So this is the, if you see 11110, that means that the data is this one. If you see 01001, the data is this one. Okay? So you have a table. So on the table itself, this is what you're going to send. So if this is what you're going to send, the number of 0 and 1 is more or less the same, isn't it? Correct? So then you won't have DC problem, you won't have synchronization problem. You see that now? So that is block coding. Okay, that is block coding. Alright, so that is block coding. So in the essence, so Wow. Okay. That's just details. So you have 4 bits. You map to 5 bits, isn't it? Correct? So what happened is that you have 100 megabits. Actually, what you need is you need a clock that is 1.2 times faster, isn't it? So your efficiency will be 80%. Correct or not? So your efficiency will be 80% instead of 50%. So from 50% it goes to 80%. Okay? So you have 16 symbol 4B. You're going to map to 32 symbols 5B. Alright? That means that you have 4 bits. You're going to map it to 5 bits. Correct? So you have 16 and 32. You still got 16 extra symbol. Correct? That is not used, isn't it? So this one you can use for maybe a line idle, or you can use for some other control thing. Okay? Alright? Line idle, reset, or whatever, you can use that. Okay? For the exact detail, you check it out in the Wikipedia. Okay? Clear? So then you can see this is line coding. I think we stop here for a while. Before that, later we go to analog.